Okay, so we're finishing up our unit talking about margins of error. So you might have heard margins of error, especially around election time when you're talking about election polls or poll results, plus or minus 3%, something like that. That's what we're doing here in this video. So the standard deviation for the sampling distribution of the proportion of voters in favor of the measure expressed by a percentage is called a standard error. So anytime you're talking about the proportion of voters in favor of something, whether that's, do they like the candidate that's running? Do they like the law that they're trying to get passed? That's called the standard error. And the standard error is given by the standard deviation divided by the number of people who were actually polled. Not the actual people who were actually voted, but the number of people who were interviewed. That's a very important distinction. In sampling and public opinion polls, it's customary to express this information about the population in terms of confidence intervals, which themselves are based on standard error. So again, the standard error was given here. For example, a 95% confidence interval is given by two standard errors below and above the statistic contained from the sample. So we're going to have a sample statistic like 68% plus or minus 3%. 68% of the people that were surveyed are in favor of the new bond error measure for the new school, plus or minus 3%. So that's what we're calculating here. It's a sample statistic plus or minus your standard error, which again was your standard deviation divided by the number of people who were interviewed, not the number of people who actually voted, the number of people who were interviewed. Let's do an example. So let's say we have an assembly line produces 100,000 light bulbs a day, 20% of them which generally turn out to be defective. Suppose that we draw a random sample of 1,600 light bulbs. What can we say about the margin of error in this sample? So first off, we're told that we're pulling out of this assembly line just 1,600 light bulbs because we're doing quality control like this. It takes time and it takes money. So we want a good sample that represents the entire population, but we don't want to do a census. A census means we look at every single possible light bulb, all 100,000. That would just take forever. We would have to shut the plant down. So instead, it's much more convenient to do a nice random sample out of the light bulbs there. Also, when we have a light bulb, we expect it to either cut on or cut off. 50-50 chance, depending on which way we flip the switch. But based on our data at this plant, 20% of them generally turn out to be defective. That's not good. So we're counting the number of defective bulbs. So this goes back to the dishonest coin principle. So if you think instead of light bulbs, we have a coin that's defective. Instead of doing heads and tails 50% of the time, 20% of the time going to be defective. So the probability is equal to 0.2. The number that we're looking at is 1,600 light bulbs. And so what we need to do first is find our average value, which remember from the previous videos was n times p, and our standard deviation was given as the square root of np times 1 minus p. All right, now plugging in what we know, that means the average value for the number of defective light bulbs is 1,600 times 0.2. 1,600 times 0.2, let's use calculator, clean that up. Which is 320. So our average value for the number of defective light bulbs out of this data set is 320. We expect, on average, 320 light bulbs to be defective out of every batch that we sample. And the standard deviation is given by 1,600 times 0.2 times 1 minus 0.2. Okay, so again, I recommend you work on the inside first, and then last step, take the square root. Just take it baby steps, that way you don't get overwhelmed. So I have 1,600 times 0.2, parentheses 1 minus 0.2. Get my number, then square root that, and get 16. So my standard deviation is 16. Okay, so now we're talking about margin of error. And remember the previous slide, the margin of error is first based on the standard error. So the standard error, what we're going to use is the standard deviation as part of it. So we need to calculate the standard error. standard error is going to be equal to 16 divided by 1600, because 1600 is the number of light bulbs that we sampled. All right, so we have 16 divided by 1600, which is 0.01%. Or sorry, 0.01, which is approximately 1%. Now, to find the margin of error, remember it's your sample statistic plus or minus your standard error. Well, in the problem, we were told that 20% of all light bulbs are defective, so that's our sample statistic, so 0.2 plus or minus our standard error that we just calculated, 0.01. That's using decimals, but typically when it's reported, we're going to talk about percentages. So 0.2 you can think of as 20% of all light bulbs are defective within a plus or minus 1% interval. So if we want to go even farther, we can say we're fairly certain that between 19% and 21% of all light bulbs are defective. Again, 20% was given to us in the problem, so the plant manager says we expect 20% of all light bulbs to be defective. We went farther and be like, all right, can we get any closer? What confidence can we give in that? So we had a 1% confidence interval, margin of error, so 19 and 21% is really where the true value is going to lie. Another example. We talk about the standard error and margins of error going to be used in anytime you're talking about public opinion polls, voting, that type of thing. So here we go. In California, a school bond measure requires a 66.67% vote for approval. Suppose that imported school bond measure is on the ballot in the upcoming election. In the most recent poll of 1,200 randomly chosen voters, 744 out of 1,200 voters sampled, or 62%, said that they would vote for the school bond measure. What are the chances that the 62% statistic is the result of sampling variability and that the actual vote for the bond measure will be 66.67% or more? Anytime you have something about school bonds or voting, approval ratings, that type of thing, we need to calculate margins of error. Okay, so let's go ahead and figure out what we have. First off, our N. N is 1,200. That's how many people were actually interviewed in this public opinion poll. Our probability, our sample statistic that was given to us is 0.62. Now, we're again going to use the dishonest coin principle because some people, when they're asked a direct question by the news media and stuff, some people kind of like to screw with the news or screw with the results, screw with the numbers. So they're going to be dishonest. Don't know why, it's just some people are that way. So you can't always rely on what people tell you and what people say on the news when they're interviewed. So we're going to use the dishonest coin principle. So what that means is our average value is given by NP, and our standard deviation is going to be given by the square root of NP times 1 minus P. Let's plug in what we know. So the average value is going to be 1,200 times 0.62. Use calculator. Give my calculator a chance to catch up. 1,200 times 0.62 is 744, which makes sense. 744 out of 1,200 voters sampled, 62%. So our average, on average, we expect about 744 of all people surveyed to say they want to approve the school bond measure. Let's get our standard deviation now. So standard deviation, again, we're just going to plug in what we know. So we have the square root of 1,200 times 0.62 times 1 minus 0.62. Using calculator, again, I suggest you work on the inside first. 1200 times 0.62, parentheses 1 minus 0.62, and then square root that. That's 16.81. I'm going to go 2 decimal places. Okay. Well, we want to know, are we ever going to get up to 66.67% or more? Because if we get up to 66.67%, then that means that the school bond that they're trying to vote on could actually pass. If we can't get there, then no matter what they do, unless they bribe people or something, most likely this poor little school bond ain't going to pass. So let's go through it. What I'm going to do is draw a sketch. This is normally distributed data, so I'm going to draw the normal curve. And what I want to do first is draw a 68% confidence interval, which means I'm going to take my mean, which is always in the middle, which was 744. And a 68% confidence interval, again, we're using the 68, 95, 99.7% rule, which means 68% means 1 standard deviation. So I'm going to go plus 16.81 above and minus 16.81 below. That's 1 standard deviation. Within that range of values, I'm 68% certain that what I'm saying is true. So 744. So 744 minus 16.81 is 727.19. Here, that's, if I go 744 plus 16.81, 760.81. So based on this normally distributed data, 68% of the voters are going to say between 68% of the data says that between 727 people and 761 people are going to say yes, they want the school bond. Let's go a little bit better. Let's say we go 2 standard deviations out. In other words, a 95% confidence interval. So here in red, that was 68% confidence interval. What we're about to do in green, we're going to go minus 0.681 again for 2 standard deviations above, and plus 16.81 again for 2 standard deviations above. Within this range, we're talking about a 95% confidence interval. That what we're saying, that what we're reporting to the media is true. So 95% confident that all voters are going to be somewhere within this range. Okay, so again, we have 727.19 minus 16.81 is 710.38. We have 760.81 plus 16.81. That's 77.62. So what we're saying here with our 95% confidence interval, which is illustrated in green, that somewhere between 710 and 778 voters out of the 1,200 that were sampled will say yes, they want to approve the school bond. Let's do 3 standard deviations. In other words, we're going to be 99.7% confident that all voters are going to fall in this range. So 3 standard deviations. That means we're going to go plus 16.81 above the mean one more time. Minus 16.81, which means we're going to go 3 standard deviations below the mean. And this is where 99, based on the 68, 95, 99.7% rule, we are now going to be 99.7% confident that all voters are going to fall within this range. So when we report this information to the media, I should say, we are essentially guarantee that what we're saying is accurate, because within this blue range, 99.7% of all voters who were sampled out of that 1,200 should fall. So what we have is 710.38 minus 16.81 is 693.57. On the upper end, if we go 777.62 plus 16.81, we get 794.343. So again, out of all 1,200 people who were interviewed, we're 99.7% sure that between 694 and 794 voters will agree on this school bond measure. Well, let's figure out of the people who were interviewed, it says we need 66.67% of the people who were interviewed to pass. So let's figure out what that actually is. So we have 1,200 times 66.67, or 1,200 times 0.6667, because 66.67% is a decimal, and that's 884 people. So what that means is we need at least 800, I forgot my decimal, 800.04 people or more out of 1,200 to pass. So at least 800.04 people must say yes to pass. Well, based on what we just drew, we're 99.7% sure that at best, only 794 people are going to say yes. So we're 6 votes short at best. At best, 100% confidence, being the most generous we possibly could be, 99.7%. We're throwing a really wide net. We're essentially 100% confident that this is true, this information is true. Okay, so that all votes are going to be between 694 and 794. We just don't have the votes. We're 6 votes short. So what that means for all the politicians and stuff is they need to be hitting the streets, going out, handing out pamphlets and be like, hey, talking up this school bond measure. This school bond measure is good. Can we get your vote? Can we get you to say yes whenever this election date is? That's what this information tells you. Politicians use this a lot. If you ever want to be a campaign manager for a politician, here you go. Now, if you're good at this stuff and you know how to work the numbers, you can make some money. So hopefully you enjoyed the videos, you learned something. If you got questions, let me know, because I want you to make some money and take me out for a steak dinner some days. Let me know if you got questions.